Hello everyone. So this is our lecture number 7, module 1, lecture number 7, and this video, this is the last topic of linear algebra in your syllabus. So today's topic is diagonalization. And this topic is very important, and definitely you will get at least one question from this topic, and that will be at least of 9 or 10 marks. 9 to 10 marks questions from this topic, diagonalization. Okay, so first of all, let me discuss you what will be the process of diagonalization. Okay, process. First discuss the process. First one, step 1. Step 1 is you have to find out the characteristic equation of the matrix. Okay, step 1 is characteristic equation. Let's say the matrix is capital A. So characteristic equation of the matrix A. Step 2. Step 2 is obviously you have to solve the characteristic equation and you will get the eigenvalue. Okay, so find eigenvalue. Find eigenvalue. Okay, now step 3. Step 3 is you have to verify that this matrix is diagonalizable or not diagonalizable. Okay, you have to verify that this matrix is diagonalizable or not. Okay, so third step is verify diagonalizability. Okay, this is the third step. Now step number 4. So if the matrix is diagonalizable, then we have to further approach for the step 4. But if the matrix is not diagonalizable, then you have to write here that the matrix is not diagonalizable. Okay, and that will be the answer of the matrix. So if the matrix is diagonalizable, then go to the next step. Next step is you have to find out the eigenvector. Find eigenvector for each eigenvalue. Okay, find eigenvector for each eigenvalue. Now step number 5. Step number 5 is you have to form the modal matrix. Okay, make modal matrix. Modal matrix means the matrix P. Okay, modal matrix P. Okay, and I will tell you what is modal matrix and so on. Okay, now step number 6. Step number 6 is, now this is your final answer, that is diagonal matrix. Diagonal matrix. Okay, so what is diagonalization? Diagonalization means you have to convert a matrix A to a diagonal matrix. And you know what is diagonal matrix? All the elements above and below the diagonal elements must be 0. Yes or no? All the elements below and above the diagonal elements must be 0. This is the definition of diagonal matrix. And the diagonal elements may be 0, may not be 0. Okay, that means we are given a matrix A, we have to convert the matrix A to another matrix B where all the elements above and below the diagonal elements are 0. Okay, now the formula is diagonal matrix. Let's say this is D, we denote it by D. D is equals to P inverse A P. This is the formula. What is P? P is the modal matrix, and remember this matrix P must be non-singular. Determinant of P is not equals to 0. Okay, now come to the main point. Main point is you know how to find out characteristic equation, you know how to find out eigenvalue, you know how to find out eigenvector. And what is modal matrix? Modal matrix means P, and what is P? Just write the eigenvectors in column wise. Okay, this is your modal matrix. Write the eigenvectors column wise, and that will be your modal matrix P. Okay, so obviously you know the how to make the modal matrix, and also you know how to find out the matrix D, because this is nothing but P inverse AP, and already you know how to find out the matrix inverse. Okay, so P inverse AP, so this is your diagonal matrix. Just you have to know in this lecture that how to verify diagonalizability. This is the unknown part in this total lecture. Okay, how to verify diagonalizability. So first discuss the verification process, then we will solve a problem. Okay, so this is equals to now process. Here you have to know two concepts, that is concept of AM and concept of GM. Okay, now what is AM? Okay, first of all let me tell you to first theorem. Suppose for the matrix A you are getting distinct eigenvalues. Okay, if you are getting distinct eigenvalues, then obviously the matrix will be diagonalizable. Okay, if you are getting distinct eigenvalues, that then obviously you will get obviously the matrix will be diagonalizable. But this does not imply that if you are not getting distinct eigenvalues, that means the matrix is not diagonalizable. No, this is not true. This is only one way statement. If you are getting distinct eigenvalues, this imply the matrix is diagonalizable. Okay, but nothing. Okay, so let me write, if the matrix capital A has distinct eigenvalues, then the matrix must be diagonalizable. Okay, so if distinct eigenvalues, distinct means different eigenvalues. Okay, so if distinct eigenvalues, so obviously it will be diagonalizable. Now question is, if they are not distinct, so what will be the process, how to check the matrix is diagonalizable or not? Process is, here we have two concept, AM and GM. What is AM? AM means arithmetic multiplicity. Arithmetic multiplicity. Okay, and GM means geometric multiplicity. Okay, AM means arithmetic multiplicity and GM means geometric multiplicity. What is arithmetic multiplicity? This is nothing but the order of the eigenvalue. Order of the eigenvalue. Okay, for example, you are getting for any matrix A, the eigenvalues are, let's say, 1 1 3. Okay, for any matrix A, let's say the eigenvalues are 1 1 3. So you can say that AM of 1, okay, AM of 1 will be 2, because here we have two eigenvalues, 2 1 eigenvalues. Okay, and AM of 3, that will be 1, because we have the eigenvalue is 1 time. Clear na? AM. Now that means the how many times we are getting the eigenvalue. This is your AM. Now let's the concept of GM. This is very, very important. GM means n minus rank of A minus lambda I. Okay, n minus rank of A minus lambda I. What is n? n is order of the matrix, order of the matrix. Okay, let's say the matrix A is 3 by 3 matrix. That means n is equals to 3. Now rank of A minus lambda I. Suppose lambda equals to 1. That means you have to find out A minus I matrix. Then calculate the rank of the A minus I matrix. Just rough work. Okay, just rough work, not a particular in process. Just rough work, calculate the rank of the A minus I matrix. Then subtract, let's say the rank of the A minus I matrix is, let's say, 1. Okay, so what will be n minus rank of A minus lambda I? What will be gm? Gm equals to 3 minus this rank 1. This is equals to 2. Okay, let's say the for the matrix I have taken the example 1 1 3 na 1 1 3. So obviously am of 1, this is equals to 2, and here I am getting gm of 1, this is equals to 2. They are equal, yes or no? Suppose the gm is 2, so 3 minus 2, that means this is equals to 1. So obviously we can say that am is not equals to gm. In that case the matrix will not be diagonalizable. Okay, so you have to check am gm property, that am equals to gm. Okay, if am equals to gm, let me write, if am is not equals to gm for at least one eigenvalue, at least one eigenvalue, then the matrix is not diagonalizable. Clear? Is not diagonalizable. Remember, I have written the word at least. Yes or no? Suppose we have 1 1 3 4 4 eigenvalues, and let's say for the eigenvalue 3 the am-gm property is not satisfying. That means am is not equals to gm. Then we can say that it is not diagonalizable. But if they are equal for all the eigenvalues, okay, if am is equals to gm for all the eigenvalues, then the matrix is diagonalizable. Okay, so remember the two words at least and all. We have to check the equal conditions for all the matrices. Sorry, this will be equal, am equals to gm, sorry, this will be equal. We have to check the equal conditions for all the eigenvalues, and if we are getting the not equal result for at least one eigenvalue, then we can say that the matrix is not diagonalizable. Clear na? Okay, let's solve an example question. Let's solve using am-gm property. Let's take the previous example. Okay, I am taking the previous example. Diagonalize the matrix if possible. A is equals to 3 1 minus 1 2 2 minus 1 2 2 0. This is the same matrix what I have taken in the previous lecture of eigenvector. You know, first of all you have to find out the characteristic equation solution, and I have just solved this equation in my previous lecture. And you know what is the characteristic equation? The characteristic equation is, you just pause the video and solve this problem. Characteristic equation is lambda cube minus 5 lambda square plus 8 lambda minus 4. This is the characteristic equation, yes or no? And after solving this equation, what are the eigenvalues? The eigenvalues are 1, 2, 2. Okay, you have to solve this equation, solve this problem in a proper process. Okay, just find out determinant a minus lambda I, then solve the equation, then you will get the value 1 comma 2 comma 2. Okay, so these are the eigenvalues. Now, so first step and second step already completed na? First step completed, find eigenvalue, second step complete. Now third step is you have to verify diagonalizability. Now for eigenvalue 1, here m of 1, this is equals to 1. Obviously they are not distinct, so we cannot say directly they are diagonalizable or not. If they are distinct elements, then we can say that the matrix is diagonalizable. So am of 1 equals to 1. And what is gm of 1? Gm of 1 will be 3 minus rank of a minus I. Formula is n minus rank of a minus lambda I. So 3 minus rank of a minus I. What is a minus I? Just calculation, rough work. Okay, a minus I, that means this will be 2 1 minus 1, 2 1 minus 1, 2 2 minus 1. So if you solve this equation, row operation. Okay, so this will be r2 minus r1, so this will be 2 1 minus 1 0 0 0, and r3 minus r1, so this will be 0 1 0. Okay, and if you change the rows, actually this is rough work, so need not to change the row. So this is pivot element, this is pivot element, yes or no? So obviously 2 pivot elements, so the rank will be 2. So this is equals to 3 minus 2, so this is equals to 1. So you can see that for the lambda for the eigenvalue 1, am equals to gm. Okay, now calculate for the eigenvalue 2. am of 2, this is equals to, am of 2 equals to 2, and what is gm? gm of 2 equals to 3 minus rank of a minus 2y. Okay, so this is equals to, what is a minus 2y? A minus 2y means you have to subtract the number 2 from the diagonal elements. Okay, so this will be 1 1 minus 1, 2 0 minus 1, and the last one is 2 2 minus 2. This is the matrix. Okay, now if you operate this, let's say r3 minus r2 r3 minus 2r1. Okay, r3 minus 2r1. so if you solve this, so this last row will be 0, and if you solve r2 minus 2r1, so this will be 0, this will be minus 2, and this will be some non-zero element, so obviously we are getting 2 pivot element, yes or no? So obviously rank will be 2, that means 3 minus 2, this is equals to 1. So you can see when lambda equals to 2, am is not equals to gm, yes or no? am is not equals to gm, so we can say that the matrix is not diagonalizable. Okay, so this is the answer, the matrix is not diagonalizable. Clear na? Now let's solve one more problem where the matrix will be diagonalizable. and we have to find out the diagonal matrix. So next problem, next question. Question, show that the matrix A is equals to 3 1 minus 1 minus 2 1 2 0 1 2 is diagonalizable. Okay, hence find the diagonal matrix. Hence find the diagonal matrix. Okay, so first we have to solve, first we have to find out the characteristic equation. First step, solution. Determinant a minus lambda I equals to 0. So or this is equals to 3 minus lambda 1 minus 1 minus 2 1 minus lambda 2 0 1 2 minus lambda, this is equals to 0. Okay, now solve this equation. So 3 minus lambda into 1 minus lambda into 2 minus lambda minus 2. Okay, minus 1 into this will be minus 2 into 2 minus lambda. Okay, minus, so this will be minus 2. Okay, this is equals to 0. That means you are getting 3 minus lambda into, so from here lambda square minus 2 lambda minus lambda, so this will be minus 3 lambda plus 2 minus 2. Okay, minus, this will be actually minus minus plus 2 into 2 4 4 minus 2 lambda, and this is 2, this is equals to 0. Okay, so 2 2 cancelled, so from here we are getting 3 minus lambda into lambda square minus 3 lambda, and this will be minus 2 lambda plus 6, this is equals to 0. So we are getting minus lambda cube minus minus plus 3 lambda square plus 3 lambda square and minus 9 lambda minus 2 lambda plus 6, this is equals to 0. So from here you are getting, okay, so this will be minus lambda cube 3 lambda square 3 lambda square 6 lambda square plus 6 lambda square, and from here minus 11 lambda plus 6, this is equals to 0. This implies lambda cube minus 6 lambda square plus 11 lambda minus 6 equals to 0. Okay, so the equation is lambda cube minus 6 lambda square plus 11 lambda minus 6, this is equals to 0. So or now if we put lambda equals to 1, so this will be minus 5, and yes, if we put lambda equals to 1, so this will be 1 minus 6 plus 11 minus 6, that means from here you are getting minus 5, from here you are getting plus 5, So yes, this is lambda equals to 1 is a root. So just one line gap by vanishing method, lambda minus 1 will be 1 factor. This is equals to 0. Multiply by lambda square. So this will be lambda cube minus lambda square minus 5 lambda. So minus 5 lambda square minus minus plus 5 lambda plus 6. So this will be plus 6 lambda minus 6. This is equals to 0. So we are getting lambda minus 1 into lambda square minus 5 lambda plus 6. This is equals to 0. Lambda minus 1 lambda square minus 3 lambda minus 2 lambda plus 6. This is equals to 0. The lambda minus 1 into here lambda into lambda minus 3 minus 2 into lambda minus 3, and this is equals to 0. So we are getting lambda minus 1 into lambda minus 2 into lambda minus 3. This is equals to 0. This implies lambda equals to 1 to 3. Okay, I think there is some background noise. Actually there is a baby who is playing. So lambda is an eigenvalue, and the eigenvalues are 1 to 3. So obviously you can see here we are getting distinct eigenvalues, yes or no? And we know distinct eigenvalue means here all the eigenvalues are distinct. Okay, so the matrix is diagonalizable. So the matrix is diagonalizable. Now you have to find out the eigenvector for lambda equals to 1, lambda equals to 2, and lambda equals to 3. Okay, so when lambda equals to 1, so a minus I into x, this is equals to 0. You know how to find out the eigenvector. A minus I into x, this is equals to 0. Just solve with me. 2 1 minus 1 minus 2 0 2 0 1 1 into this will be x1 x2 x3. This is equals to 0. Now convert the matrix. Actually this matrix will be the coefficient matrix, so just I am calculating. Okay, 2 1 minus 1 minus 2 0 2 0 1 1. Okay, just convert this matrix into row echelon form, R2 plus R1. So this will be 2 1 minus 1 0 1 1 0 1 1. Next R3 minus R2. So this will be 2 1 minus 1 0 1 1 0 0 0. So obviously we have two pivot element 1 and 2. So obviously there exist unique solution. So what are the solutions? What are the system of equations? 2x1 plus x2 minus x3, this is equals to 0, and x2 plus x3, this is equals to 0. Okay, and here x3 is free variable, so put x3 equals to k. So this will be if x3 equals to k, then x2 equals to minus k, yes or no? And x1 equals to x3 minus x2 divided by 2. So this is equals to k minus x2. So this will be 2k divided by 2 equals to k. That means the eigenvector is x1, that means k, x2, that means minus k, and x3, that means k. Now if we put k equals to 1, so you are getting 1 minus 1 1. Clear? This is 1 minus 1. This is the eigenvector for lambda equals to 1. Okay. Similarly, find out the eigenvector for lambda equals to 2. For lambda equals to 2. Same concept. So a minus 2i into x, this is equals to 0. So the matrix will be 1 1 minus 1 minus 2 minus 1 2 0 1 0. Okay, into x matrix, let's say x1 x2 x3, this is equals to 0 0 0. Okay, so this will be the coefficient matrix 1 1 minus 1 minus 2 minus 1 2 0 1 0. Now operation is r2 plus 2 r1. So this will be 1 1 minus 1 0 1 0, and the last one 0 1 0. Same r3 minus r2. So this will be 1 1 minus 1 0 1 0, and the 0 0 0. Okay, obviously this is in row echelon form, and 1 1, these are the pivot elements. Okay, so the system of equations are x1 plus x2 minus x3, this is equals to 0, and x2 equals to 0. Okay, is this correct? Yes. So obviously in this equation there will be infinite solution. x3 is free variable, x3 is free, so let x3 equals to k. So you are getting x1 equals to x3 minus x2, so that means this is equals to k. So for lambda equals to 2, the eigenvector is x1 k, x2 0, x3 k. So if we put k equals to 1, the eigenvector will be 1 0 1. Clear? 1 0 1. So this is one eigenvector. This eigenvector is for lambda equals to 2. Now calculate for lambda equals to 3. For lambda equals to 3. So a minus 3i into x, this is equals to 0. So the matrix will be 0 1 minus 1 minus 2 minus 2 2 0 1 minus 1 into x1 x2 x3, this is equals to 0 0 0. Okay, so coefficient matrix is 0 1 minus 1 minus 2 minus 2 2 0 1 minus 1. Okay, here first row is 0 na, first element is 0, so we have to interchange second row and the first row. So r1 interchange r2, so this will be minus 2 minus 2 2 0 1 minus 1 0 1 minus 1. Okay, so r3 minus r2, so minus 2 minus 2 2 0 1 minus 1 and 0 0 0. Obviously this is in row echelon form. This minus 2, this one are pivot elements. Okay, so obviously there will be infinite solution because rank is less than 3. Okay, so what will be the system of equation? Minus 2x1 minus 2x2 plus 2x3, this is equals to 0, this is the first one, and x2 minus x3, this is equals to 0, this is the second one. Okay, and x3 is free variable, x3 is free, so let x3 equals to k. Okay, so x2 equals to again x2 equals to x3, so x2 equals to k, and what is, so minus 2x1 minus 2k plus 2k, this is equals to 0. That means you are getting x1 equals to 0. Okay, so what is the eigenvector? x1 0, x2 k, and x3 is k. Okay, if we put k equals to 1, so you are getting 0 comma 1 comma 1. Okay, that means here we are getting 3 eigenvectors for lambda equals to 1, lambda equals to 2, and lambda equals to 3. Now we have to form the modal matrix. Okay, so next, so the modal matrix is P is equals to, we have to write the eigenvectors in column wise. What was the first eigenvector? This one, na? 1 minus 1 1, so we have to write in column wise. So 1 minus 1 1. Okay, next eigenvector, this one 1 0 1, so write 1 0 1. Next eigenvector, this one 0 1 1, so write 0 1 1. This is your modal matrix P, and I already have told you that the matrix P must be non-singular. Determinant of P must be not equals to 0. You can verify that the determinant of the matrix P, that will be non-singular, non-zero. Okay, now you have to find out P inverse. Okay, P inverse, you can use any approach to find out the P inverse in this problem. Okay, if the question is question is find out the inverse of the matrix, then you have to use the Gauss-Jordan method. That means the right hand side will be identity and you have to make left hand side identity, that process. But in this diagonalization process you can use any approach. Okay, P inverse, so I am using the adjoint of P by determinant P. Okay, so what will be adjoint of P? So this is equals to, actually what is determinant P? Determinant P equals to, so this will be minus 1 and this is 1 minus minus plus 1, that means 2, so this is equals to 1. So determinant P is equals to 1, and so what will be adjoint of P? So this first one element, for the element 1, so this minus this, so minus 1. Okay, now for the element this, so this will be minus 1 minus 1, that means minus 2. Yes or no? Is it correct? Yes, minus 2. Okay, now for the element 0, for the element 0, so this will be minus 1 minus 0, so this will be minus 1. Okay, now for the element third element, this minus, so this will be 1 minus 0, that will be 1. Okay, now this element, for this element this will be 1 minus 0, so again 1. Now this element, so this will be 1 minus 1, that means 0. Okay, now this element, so this will be 1 minus 0, that is 1. Now next element, this one. Okay, so for this one, that will be 1 minus 0, that is 1. Okay, and the last one, this element, so this will be 0 minus minus plus 1, so this is equals to 1. Okay, now we have to adjust the sign. Adjust the sign. The sign process formula is minus 1 to the power I plus j. Okay, minus 1 to the power I plus j. So 1 plus 1 2, so minus 1 to the power 2, that means even, so this will be plus, again this will be minus, so minus minus plus, this will be, so plus minus plus, this is minus, and this is the position 2 1, that means odd number, so this will be minus, this is the position 2 2, so plus, this is the position 2 3, and 0 plus minus same, this is the position 3 1, so plus, position 3 2, so this will be minus, and position 3 3, so this will be plus, and the transpose of this matrix, then that will be adjoint. So this is equals to minus 1 minus 1 1 2 1 minus 1 minus 1 0 1. Okay, this is your adjoint matrix, and determinant p is 1, so division will be same as the adjoint matrix. Okay, so this is your P inverse matrix. Now you have to find out the diagonal matrix D. D is equals to P inverse AP. Okay, D is equals to P inverse AP. So this is equals to, what is P inverse? Minus 1 minus 1 1 2 1 minus 1 minus 1 0 1 into the matrix A. A matrix means 3 1 minus 1 minus 2 1 2 0 1 2, and the last one 1 1 0 minus 1 0 1 1 1 1. Okay, you can product any two of the two matrices. Okay, first I am producting the first matrix and second matrix. Okay, so this will be minus 1 into 3 minus 3 minus minus plus 2, so minus 3 plus 2, that will be minus 1. You can calculate yourself. So this will be minus 1 minus 1 1, this is 4 2 minus 2 minus 3 0 3. Okay, this is the product of the first two matrices into the last one 1 1 0 minus 1 0 1 1 1 1, and this is equals to 1 0 0 0 2 0 0 0 3. Okay, this is the product, and this matrix, this is the diagonal matrix of the matrix A. Okay, and this is the final answer. Clear? So in this way you have to solve the diagonalization problems. Obviously these type of problems are very lengthy problems, and it will contain at least 9 to 10 marks each problem. 9 to 10 marks each problem. Clear now? So now you have to try your question bank problems and previous year question papers. Thank you so much.